All right, math 21. What are we doing here? We're on like day 8 or day 6 lecture. This back pen is already dead and I toss it. We are doing 3.2 and 3.3 today. 3.2 is on dispersion. So I have a quick activity for you. I have two groups, A and B. A has numbers 46, 48, 50, 52, 54. And B has numbers 10, 30, 50, 70, and 90. Find the mean for each group. Give you like 30 seconds to calculate it. This is quick calculator work. What'd you guys get? 50 for both, right? A was 50. That's my red slashes on my number line right here. And B was also 50, and that's my green little asterisks down below. If we put them on a number line. Like the red ones are all really close to the 50. That's option A. Option B, they're really spread out. We got numbers almost 0, and we got a number close to 100. So mean doesn't tell us everything. Doesn't show the whole picture. It doesn't show how spread out the data is. I got your email and I'm going to do it in class. So this is where dispersion comes in. Dispersion is a measure of how spread out the data is. Alex, you write it where the letters are bigger so they're easier to read. Or how much it deviates from the mean. One of the simplest ones is called the range. The range is largest value minus smallest value. Yeah.
What's the other word for deviate?
Differ. How much it differs from the mean? Or I could give you my brother's name, he's a deviate. Nah, that's a joke. That's deviant, isn't it? When we make it a noun, it's deviant. So for group A, the largest number is 54. And the smallest number is 46. So if I subtract these, I have 8. What about B? What's the range for group B?
80,
How'd you get that?
90 minus 10.
90 minus 10. 90 is the largest one. That matches up with what I see here. 10 is the smallest one. 90 minus 10 is 80. So the bigger it is, the more spread out it is. The bigger the range, the more the spread. Is ready for more? If you need it up longer, let me know, or I'm gonna pull it in 3, 2, 1. All right, not saying anything. Okay. So I want to tie this into something we had the other day. We were talking about resistance. Resistant stats were not affected by outliers. Not affected much by outliers, I should say. So what if A was 46, 48, 50, 52, and then 154? So this is like a what if the 54 was 154. What's my range now?
Oh, your last one, the range was 8.
The last one, it was 8. What is it now? It's 108. If we do 154 minus 46, all I did is added 100 to the largest number. So our range should have jumped by 100. So the range went from 8 to 108. This means the range is not resistant. In fact, of all the different measures of dispersion that we're going to do over the next few classes, it's probably the least resistant. For bell-shaped graphs, we like to do something different. Like ranges probably works well for uniform graphs. We use standard deviation. Or just deviation. It's technically standard deviation the whole time. Just like that gets it takes it a while to say after a little while. When you're saying it 80 fucking times, you're like shedding time off your life. So we just shorten it down. Okay, so this is different for populations and samples. The population deviation is what we got to do is we got to take each of our data values. Xi is our data values. Oh, and we're going to subtract the mean, which is mu, and we're going to square it. Then we're going to add those up. Then we're going to divide by the population size. And then we're going to take the square root. Right? It's a fucking lot. Xi is the individual data values. Mu is the mean. The crazy E means add shit up. It's the summation notation. N is population size. That's fucking tedious.
And that's the equation you will use when you find the population.
When you're finding the population. The sample standard deviation is different. Not a lot different. Let's get the panic out of the way right now. We're not going to calculate it in hand. We're going to do stats, summary stats, and columns in StatCrunch. I'm not going to make you do that by hand. Maybe Michaela.
So basically, we do this.
Yeah, we're gonna do it. We're gonna do it with like 200 people, and we'll find the fucking standard deviation for height. We'll do that in a second. Now, the sample deviation is a little different. But not a lot. We still have Xi. We are still subtracting the mean, but the mean for a sample is X bar, not mu. We're still going to square it. But instead of dividing by the sample size, we're going to divide by the sample size minus 1 before we take the square root. So X bar is the mean for the sample here. And little n is sample size. N minus 1 has a name. N minus 1 is called the degrees of freedom. And it shows up enough in that they abbreviated D period F period. It even has that in StatCrunch. It'll say put in the degrees of freedom, which is stupid. It should just have the sample size. But yeah.
The full survey of the people, so you're subtracting, so what you're saying is whatever sample you have of both persons, you have to subtract by 0.
Whatever sample size we have and we're using it, we have to use one less. So if I survey 30 people, I need to use 30 minus 1 is 29 on the bottom. Does that make sense? The n minus 1 is kind of forces this. This is very mathy, so I'm just gonna be a little hand wavy with the explanation. It forces the final one, like everything else is gonna have to do its own thing. But the final one, we should have like the mean be the mean. And it forces the final one to be a certain way. That. It's kind of like. Let's do this. I've got 3 color pins here, blue, red, and green. Which color do you like?
Green.
You like green. You can't pick it, or you pick it. Angie, which color do you like? You like red. Did you get a choice?
I was gonna say, green.
That's not the question.
Did I get
You have a
it?
choice.
No.
You do not have a choice. It happened to me, she liked blue. She was not free to pick her answer. So n was 3. 2 of them were free to choose, the last one was not free to choose. That's about as simple as I can make it. Don't worry too much about it, just know that it's the sample size. You just subtract 1 from however many people are in the sample. You just subtract 1. So both of these, you can see that we kind of need. We need to have the data. Because that's all of our xi. And if you have all the data, actually the rest can be calculated. We can use the data set, we can calculate the mean with it. And we can calculate the sample size with it. Or calculate the group size. If it's not a sample. So you can't have like summarized data. We can't have like 20 people said, I like morning. We didn't know like individual, like have each response in there. And it only really works for like morning isn't a good choice. This only works on numbers. Because we can't take like the mean of a category. So just like mean, standard deviation only works on numbers. This only works on numerical data. A big reason for it is it depends on the mean. And that uses numerical data.
Also known as quantitative.
Quantitative data. Someone's showing off. I approve. Why are you sitting in the back? Usually the show-offs are in the front row. Right? Or the people that can't see well.
Yeah, that would be me.
And so what we will end up seeing is the greater the deviation, the greater the dispersion. We call that being less consistent. And there's a simple reason why we call less consistent. Let's go back and look at those dots that we had on that number line. The red one consistently got around 50. Like if this was like smaller numbers, like let's say this was 5 and close to 5, and this was like 1, 3, 5, 7, and 9. Let's say you're fucking catching fish, trying to feed your family. You want to consistently catch enough fish to feed your family. You don't want to have one day where you're fucking pulling in 9 and you got a lot of extra, but then the next day you catch 1 and your fucking family is fighting over a single goddamn fish. You're not consistent with how many fish you're catching. But if you're catching close to 5 every day, you're consistent. So that's why we say spread out is less consistent. Before we look at it in StatCrunch, there's something else to note. So in StatCrunch, they list population deviation and standard sample deviation differently. The one that says std.dev is sample standard deviation. And I don't know about you, but I think they fucking don't know how to abbreviate very well. Like, I don't know why they chose STD. They had to know what it looks like. If it says UNADJ STD dev, this means unadjusted. It's shortened for unadjusted. This is the population standard deviation. Because the formulas are different. So they have to, the bottom is different. Remember, one subtracts 1 and the other one doesn't. I'm going to say roughly 99.99% of the time, you will use the first one. std.dev. In fact, when we look at it, I'll show you unadjusted standard deviation is at the bottom of the goddamn list. They want you to click on it on accident because it changes the result. Doesn't change it by a lot. And I'll show you, but it changes it by enough that they don't like it. I didn't give the fucking symbols for these. Oh my God, fucking failed. Population deviation goes by lowercase sigma. It looks like an O with a really long tail on it. This is called sigma. Sample deviation, they're so fucking clever, they call it S. S for standard. You'll find that for most of the shit for populations, we use Greek letters. And if it's an American letter, it's for a sample. The reason why I remembered to bring that up is because there's something highly related to standard deviation called the variance. But the variance is just the standard deviation squared. So sigma squared or S squared, depending on if you're talking about population or sample. You guys ready to see it in StatCrunch? So I got my data right here. This is the table we've been using for everything. I'm gonna go stats, summary stats, columns. I'm gonna do height. And we'll take a look at the mean, the standard deviation, the variance. And I think I'll come down here and I'll look at that unadjusted variance and unadjusted standard deviation are damn near at the bottom of the list. They're way at the bottom. So this is talking about the mean height in inches. It says 52.73. It says a standard deviation of 26. 26 is over 2 feet. And the variance is that number squared. And look how close the unadjusted is with the one that says is just regular. We got 26.372 and we've got 26.310. They're pretty close. This seems like a big red flag to me. People don't deviate by so much that we would call it over 2 feet. If I look at height in inch, every 12 inches is a foot. So 5 feet is 60 inches, 4 feet is 48 inches. This is saying that the average person in over 200 people, the average height is under 4'5" inches. Does that seem realistic to you? No. Like, how many people do you actually meet on a daily basis that are below 5 feet tall? No, adults. So let's not talk about children, adults.
Yeah.
Not that many, right? Most everybody. I mean, there's some. There tend to be more women that are shorter than men. But still, there's not enough that you would, that's just under 5 feet. I don't think I hardly ever see, like maybe once every 6 butts, I might see someone that's under 4'6". That's like really, really tiny. So the mean looks like it's off. And if I come and go look at the data real quick, like I'm looking at height, I got 60, that seems okay. 72, that's 6 feet tall, that's about right. 5.07. I have a very strong suspicion that no one took this survey is 5.07 inches tall. I've never met not even a baby is 5 inches tall. They're all tall, bigger than that. I'm guessing, what do you guys think they meant by this? They might have meant 50.7, maybe. I strongly suspect it's 5'7" inches though. So like this is what's throwing it off. If you encounter this when you're like working with data, you have a couple options. If there's a lot of data, you can just like delete those rows because the answer clearly is not true. There's no way someone that was 5 inches tall replied to this. Unless there's fucking pixies, unless Tinkerbell fucking exists and she fucking surfs the internet. She didn't answer. And if it's surveyed person, I guarantee whoever's doing the fucking survey is going to notice if someone 5 inches tall is fucking taking it. Right? They would come back and you would tell somebody about it. I met someone that's 5 inches tall today and they'd be like, you mean 5 feet? I said, no, 5 inches. So we can either delete them because we don't know for sure that they meant 5'7". They could have meant 50.7. Or we can make the assumption that it was 5'7" and just change it. 5'7", 5 feet is 60 inches. 7 more inches would make that 67. And I could go through and do that for all. 5.4, it could be 54. But the decimal, I don't know why they would have accidentally hit a decimal point for this. I strongly suspect this is 5.4 inches. So I could change that to 64 inches. And I can go through and do it all and then recalculate the mean. The two things for them to take away from this lesson were, we can get it through stats, summary stats and columns. And you want to use standard deviation and pick the category. Unadjusted is for populations, very rarely, unless it says populations, you don't use this. The second takeaway is, don't always just accept what the computer spits out. Stop and reason it out. Now, most of you will probably not jump to recognizing 52 inches is under 4'5". But maybe having 26 inches, 2 feet deviation, that means you on, like, if the average person is 5.5 feet tall, you frequently meet people that are 7.5 feet tall and people that are 3.5 feet fucking tall. And I really don't think I've ever met someone that was 3.5 feet tall. I've known some dwarves. No, they're probably close. Diminutive people, I don't know. I don't know the right terminology. I'm in that old group that just uses names. So sometimes like go, does this sound realistic? Okay. That's how we're gonna do it. We could do the same thing with the standard deviation on shoe size. But before I do that, I'm gonna look at a distribution on shoe sizes. We'll let them bin it. Oh, I wanted a graph. Graph is easier to see. All right, so I got a couple shoe sizes. Holy fuck, are there shoe sizes less than 5?
Yeah,
For adults?
yeah, mom's like size 4.
No shit.
Yeah,
That's a tiny foot. Like if they try to kick your ass, they gotta like do a lot of kicking. Because there's not a lot of surface area to kick your ass with. Holy shit. Look at this motherfucker. 16. Fucking circus clown shoes. I think I know who that is. I think it's many of these were former students. I had a student in here. He easily was fucking 7 feet. Like he'd walk down the hall and you'd be like, is this whole fucking, you'd see him in the distance, you'd be like, is there a lot of fucking children here? Because you see the tall one, you expect the tall one to be the adult. And then like anybody that's like fucking comes up to, you know, belly button is probably a child or mid chest. Nope, when you get closer and he's fighting, you're like, oh fuck, what's the weather like up there? I haven't seen Dominic in a while. He was good people. He was smart.
When I was a freshman in high school, there was a senior who was 7'4",
That's a big motherfucker.
and then his older brother was 7'8".
That's a bigger motherfucker,
Yeah,
right?
they were huge.
But would I call them a big motherfucker to their face? Probably not. Maybe Dominic. Dominic wasn't tall, but he was like a beanpole. He was slender. Yeah, he's lanky. Lanky's the right word. I wasn't physically intimidated by him. You get that fucking linebacker that's basketball players tend to not be lanky. They tend to look fairly muscular. I don't want to fuck with that. I don't want them to accidentally think that motherfucker, for me, was a bad term. Like if I say motherfucker, the only time it's a bad term is if I sound angry. Otherwise, it's just like saying very or pretty or ugly. It's an adjective. All right. So there's our shoe size like distribution. And let's go take a look at what the summary stats look like for it. It says the mean is 9. That looks about right. That looks like it's right about here. Fuck, it is right there. The mean is 9. Standard deviation is 2. So when you go 2 units higher up to 11, or 2 units lower over here, you generally don't have, you still have data outside that region. You guys see that? Like here's the 7. Having a 2 is putting it just right here. which means this column, this column, this column, and this column are still to the left of it. And when I have go 2 columns to the right of here, anything higher than 11, this is like anything higher than 11, really. So these 4 columns and that column over there. One deviation doesn't capture all of the data. Let's take a look at how that works a little bit better on the empirical rule. So the empirical rule is a graph. And it is a graph you should probably memorize. I'm going to assume I do a decent bell curve here. Not bad. What we have in the middle for a bell curve is the mean, or X bar, if we're doing samples. If we go out 1 standard deviation, it's right about there. So this is like adding +1 deviation. So this value right here is actually the standard deviation, or the mean +1 deviation. And if I go the other direction, I'm subtracting 1 deviation. So this is like mu minus 1 deviation. This is called the empirical rule. Then if I add another deviation, plus 2 deviations this way, or a total of, I should write just +1 more. This puts us at 1 more above 1 deviation. This is 2 deviations.
Is that like a sigma sign or a 10?
That's the sigma sign. It is 1 sigma. Thank you for asking. And all of these arrows should look the same length, but I'm not a fucking artist. Get over it. Fucking 4. How big is a 4 shoe? It's like, can't be inches. How do they measure the size?
Yeah, women's is a little different than
Yeah, women's shoe size, I don't, that's, which is stupid as fuck.
5 smaller. Yeah,
What idiot came up with this?
well, like the European thing was like 44 or like 30.
Yeah, but why not just be consistent? That way anyone can wear anyone's shoe. Like, let's face it, other than color, a tennis shoe is a fucking tennis shoe.
There we go.
You can tell the difference between 2 tennis shoes,
But yeah,
other than color, really? Like, can you tell the difference? If we had a guy's tennis shoe and a girl's tennis shoe the same color and roughly the same like size, without looking at what the shoe size says, could you tell which one's female and which one's male?
It's just like more narrow, men are more wide.
Really?
kind of like the soles too. Because women's soles tend to be a little thicker in the bottom. But that's like a men's shoe, like
Huh.
Converse, Band.
That's crazy. Maybe I don't know what the fuck I'm talking about, and y'all do. There's a good chance of that. I don't go around measuring shoe size, so. And I don't know anyone with a shoe size of 4, so I don't have any fucking source of reference here. All right, we're gonna go the other way. We're gonna subtract 1 deviation at a time going to the left. And we're gonna have mu minus 2 standard deviations and mu minus 3 standard deviations. This is the base graph. Now, the entire area under the curve is 1. And it doesn't matter which standard deviation shape we use. We can have tall ones, we can have short ones. So the area has to remain consistently 1. But no matter what happens here, whether we have a tall standard deviation or a short deviation, between mu and mu plus 1, 34% of the data is right there, and 34% is over here. So going between plus and minus 1 deviation gets you 68% of the data. Usually. It's approximately, it's a good measure. And now if I go to the next region is much smaller in size than the 34%. This is actually only 13.5% here. And it's the same thing over here between -2 and -1. If you add up 13.5 and 13.5, you get 27. And if I add the 68 to it, I get 95. Between 2 standard deviations, plus or minus 2 deviations, you will get 95% of the data. This is an approximation. The actual value is like 95 point something. We'll see that when we get to chapter 7. Which means there's only 5% left for the rest. Or outside of 2 deviations. Which means there's like, this region over here is 2.5%. And this region over here is 2.5%. Half on each side. Because it's got to add up to 100%, right? We can't have 110% of the data. That doesn't make any sense. What these break down into right here for the 3 deviation marks. This one is 2.35. And this is 0.15. Which means it's the same thing on the other side. 2.35% and 0.15%. Which means if we add up between 3 deviations, within 3 deviations, we get 99.7% of the data. 99.7% of the data is within.
So it's kind of like as you go like more outside the middle, it gets smaller. Of the
As you get away further away from the middle, yes, each area gets smaller. But this distance between the distance you're going from each group is the same distance. I'm going to do an example where we do intelligence quotient IQ test here in a second. And we're going to actually put numbers on the line so you can like actually see a little bit better what's going on. Generally, this outside of the 5%, this is where we call the outsiders. And this is where outsiders are. Or not outsiders, outliers. That looks like an OUH outlier. There we go. You guys ready for, I see some pins still gone. Barking spiders are bad this time of year. Alright,
The previous sheet underneath variance equals the standard deviation to the second power, we need a secondary last. Thank you. Thank you.
actually, I don't wanna move this, I'm gonna leave this where we can see it. And I wanna talk about the standard IQ test. So the standard IQ test. You can actually take it at stanfordbenet.com. They're the people that invented it. But not Benet, but stanfordbenettest.com. There is a quick version and a regular version. The quick version is only 12 minutes and you have 50 fucking questions. The regular version is 24 minutes and you get 100 questions. If you decide to go see what your IQ is, try to look at the end score and not like at how many questions you do. I took the full length one and I got like fucking, I don't remember, it's been a couple years, but it was like 20 questions done out of like 100. I felt stupid as fuck. I'm like, really? I could only answer 20% of them? They got us make so many questions that like Einstein can take it and still take the full 24 minutes. I bet Einstein would sit down and bust out like 20 questions in like 5 or 6 minutes. He's like super genius, super smart. So like it measures it, and it's more on how well you work with numbers and comprehension in reading. Like what do you pull out of reading? So like there's some of those questions have like paragraphs and like it's respond. And like I don't know how you're supposed to answer a fucking lot of questions in it. But I had above average score and I didn't have a very high percentage of questions done. So don't look at questions you completed done as a measure of how smart you are. Just look to see that IQ. And then always remember it's measuring your abilities with math and grammar, basically. But when people take this test, the population standard deviation or the population mean is 100. The standard deviation is 15. Which means if I want to copy or set up the empirical rule for the IQ test, I'm going to put the mu in the middle. The 100 is our mu, that's our average. I'm going to put it in the middle. And as I go to the right, I'm going to add the value of the deviation. So the standard deviation is 15. I'm going to add 15 as I go to the right. And I'm going to keep doing it. I'm going to do it 3 times. That'll give me a 130 there and a 145 here. Maybe I should put them above it, since I've done fucked up the bottom already. When we go the other way, we subtract 15 each time. $85, $70, $55. So like, when you get a question like this on the homework, what they're gonna do is they're like, homework questions will be like this. The IQ test has a mean of 100 and a standard deviation. And they might spell out those words mean and standard deviation of 15. What percentage of the population has scores between 70 and 115? And they are not gonna give you that fucking chart right there. No chart right there. Just the question. To kind of answer this, you really need to draw the chart. Because once you draw the chart, you have the percentages for each region. 34% here, 34% here, 13.5, 2.35, 0.15. Those percentages always are the same, no matter what shape the graph is. So what do we gotta do? We identify where the 70 is. And we identify where the 115 is. It's this region right here. So 70 to 115 it's got 13.5% plus 34% plus 34%. And if you add those up, I think that adds up to 81.5%. They'll give you two numbers and you got to give the empirical range values. Okay. This actually leads to one of my favorite questions ever. What percentage of people are below average intelligence? It's generally not a question, it's a statement. They actually fill in the percentage. Well, average means mean. So we're looking for below the mean. (0.15% plus 2.35% plus 13.5% plus 34% equals 50%. Half the people you meet every year are below average intelligence. Now, generally at college, that number is higher. Because people that like hate math and English and history and all those like school subjects don't go to college. Like the people that wouldn't do well on the IQ test are frequently the same people that don't go to college. Not always true. I'm sure my brother would do all right in mathematics. He's nowhere near me, but I'm sure he could pull. He does plumbing. He's got to do like work with fractions and shit like that all the time. There's a lot of fucking gritty math work in plumbing and electricity and shit. So he's got math skills, and he didn't go to college, so it's not true of everybody, but in general, below half. And at college, above half should be, or below half at college should be below 50%. You should meet more than 50% that are above. All right. Oh, something else to point out here. Couple things I wanted to point out. Does anyone need that? Oh, wait, I see people still writing. They'll ask you all sorts of number ranges, but every single number should be one of these numbers that you put down below. They might go 55 to 130. They might say 100 to 130. And it may not even be related to IQ. I know one of the problems they like to do is the average number of chocolate chips in a bag of chocolate chips, which is a surprisingly large number. And they will do the mean number of chocolate chips in a bag and then the standard deviation. They'll have you do something like this with that. They got a couple topics for questions they like to use. I think chocolate chips is a good category. All right, so standard deviation, there's a couple ways of looking at this. I'm going to draw the number line again real quick. We had 100, we had 115, we had 130 and 145. And the chart we had was like that. So the black line is mean of 100, standard deviation of 15. What happens if the standard deviation goes up? What if it's still a mean of 100, but the standard deviation is like 30? Well, it has to start at a lower value because it's going to be a little bit higher up out here. So this would be this isn't exact because I'm just like sketching a situation, but it's definitely going to be shorter. Picture this like a sandbox. There's like a specific amount of sand in the box. You could pile it all up in the center, and if you like use water and like pack it, you could make like a tower that's like pretty narrow, right? But eventually that shit dries out and it eventually falls down and the sand falls down and fills up the outer regions. But the sand's got to go somewhere. If the pile in the middle of the sandbox goes down, it's got to be spreading out here and making the areas out here taller. So this went down, but out here it went up. The amount of sand in the box has to stay the same. And it's not sand, it's data. I got one more thing to show you. I'm not going to work out a problem using it. I'm going to show it to you. We'll take a 5-minute break. 3.3 is not actually assigned homework, and I'm not testing you on it. It is on weighted means. which is how GPA is calculated. It's a pretty good thing to know how to calculate and where it's coming from and what it means to you, like if something's gotta give, like something comes up, grandma gets sick, and you gotta like drop one of your classes, what's the best choice to drop it? But since you're not being tested on it, like after when I say let's take a break, if you don't give a shit, you're free to go. Cause you're not gonna be tested on, there's no homework on it. I am also gonna go over a problem from 2.4. Where there was a graphing thing and it was on. Like, how could we redraw a confusing graph? It was one of the homework problems. But before I do that, I want to talk about for non-bell-shaped distributions. We use this, and I'm going to write the name first before I say it, because you'll never guess how it's spelled by the way I say it. Chevy Chev. Chevy Chev or Chevy Chev? I'm not sure, but both of them fucking sound great. I like Chevy Chev better. I have no idea how it's supposed to be pronounced, but kind of like just flows off the tongue. Like Mufasa, Chevy Chev. Well, maybe not like Mufasa. So Chevy Chev's inequality requires, it looks at the area within K deviations where K is a number greater than 1. So what it is the percentage of data within K deviations is I think I'm missing something here. It's 1 minus 1 over K squared. Then we multiply by 100% to make it a percent. So the percentage of deviation data within K deviations is less than this. That's what I'm missing. Now, I don't think there's any problems on the homework that have it. And this weekend I'll look over if they do, and if they do, I'll talk about it on Tuesday. Like Chevy Chev isn't all that exciting. It doesn't happen all that often. You'll see as we go through this class, most of the data we end up working with, when the way we work with it ends up being bell-shaped. So that's the big takeaway. If you wanted to make one more note about the empirical rule, plus or minus 1 deviation is 68%. Plus or minus 2 deviations is 95%. Plus or minus 3 deviations is 99.7%. I mean, we showed that on the other graph underneath it, but I think having it all put in one area makes it a little bit easier to remember. And the percentages go 34%, 13.5%, 2.35%, and 0.15% moving outward. Other than that, let's take a break. 5-minute break for people that need to use the restroom. So 3.3 is on weighted mean. There is no homework in this category. And they are not on the test. But I think it's at least very useful for students to see once. The weighted mean is it goes by X bar with a W next to it. And the way they calculate it is they add up all the weights. So they use WI, the individual weights. Individual weights. And on top, they multiply each individual weight multiplied by the value that goes with it, and then they add it up. That's the generic form. I think this gets a little clearer if I start talking about GPA. The bottom is your total number of units. The top is your units, which is the weight times your grade. That should say grade right there. So let's talk about how the grades work first, like make sure like you guys are up on it, like your letter grade and the value that we have. Let me just write a list of the letters. And I think if I do those, you'll get the idea past it. I'm gonna put C minus here in red because I'm gonna say no right here. I don't think universities are forbidden from giving out C minuses, but community colleges by law can't give you a C minus. Because someone thought it was demoralizing or something. I have no fucking idea. Like saying a C minus means you did less than what they consider passing. But I don't know. Like, I have no fucking idea. It doesn't make any sense to me. A fucking politician came up with this.
Barely passed versus
Right.
actually passed.
You barely be like scraped through versus like you did a little bit better than scraping through.
Yeah.
Like 79% is a B plus or a C plus. A 71% is a C minus. So like, but like a 74 is a C. So like 71% and a 73% is a C minus. So it's a fine distinction. All the whole letter grades are worth whole value points. A is 4.0, B is 3.0, C is 2.0, and D is 1.0. The minuses are all 0.3 lower than it. So we'll have a 3.7 and 2.7. And I can't do a C minus, so no 1.7, but the D minus is like 0.7. And when we go up, oh shit. Is it 0.3 or 0.4 above it? You think it's 0.3?
Yeah, I was getting for that to test, the success thing.
3.7, 3.3, yeah. So going above it, like you go down, it's minus 0.3, you go up, it's 0.3. So if I add 0.3 to 3.0, I get 3.3. If I add 0.3 to 2.0, I get 2.3. If I add 0.3 to 1.0, I get 1.3. If you go from an A to an A plus, they say go fuck yourself. You're only getting a 4.0. You don't get nothing special for the A plus. Now, there are plenty of colleges that will say, like, students with a GPA of 4.2. Either they are weighting A+ is higher, or they're trying to say like an AP course at high school should be worth more weight than the equivalent course at a college. AP calculus at a high school versus calculus here. Then you like if you get an A in AP calculus, it's like a 5.0. Rather than here, it would be a 4.0. So it's like if you did it in high school or not. Like I've seen plenty of smart students come here. I've seen students that are like 17 taking Calc 3, like end game fucking math. And like I'm like, if your school just offered this, you could do AP calculus the whole way and have a super high fucking GPA. It's kind of bullshit. Like generally the AP Calc classes, they're actually don't teach as much. They're less educational than just attending a college course. We have higher standards at college. Well, we're supposed to. All right, so that's how we're gonna do it. So let's say you're taking, you got Math 21. I know you're taking that. That's 4 units. Let's say you're taking English 1, because you're like, fuck it, I'm gonna get rid of all the shitty courses all at once that I don't want to take. And then you're like, you know what? I'm an art major. I fucking love Art 01. I don't know, maybe Art 02. But art classes are only 3 units. And then there's like an academic library fucking / study one. It's only 1 unit. It's like how to study better, how to use the library, how to do stuff like that. It doesn't take 3 hours a week. It's a 1 hour a week course. Let's say shit happens. Your job fucking ups your hours. You get like a pay cut or something happens, you lose a couple hours. So you have to take a second job and you end up working more hours than you did before. Someone in your family gets very ill, like an elder or like children, if you got children. Point is, you're not going to be able to get an A in every class, no matter how hard you try, because you don't have time. So let's look at a couple scenarios. Option 1 will be you get the A's in math and English, and you get like, we'll go with a C in art and a B in library studies. And then option 2, you're like, nope, I hate fucking math. I'm gonna barely get a C. English isn't much better, we'll get a B there. I love art, and the library shit's kind of easy, so I'm gonna get an A in those courses. And let's say this is your first semester, so they're not checking any other semesters. When they do your overall GPA, like after you've been here 4 semesters, they do this for every single course, what we're about to do for 1 semester. Option 1, let's explore what happens. Well, the A is 4.0. And I use nice whole numbers to do these relatively easy to make the math a little bit easier. And B was a 3.0. So our GPA, this adds up to 12 units. That's important to know. That's what goes on the bottom, 12 units. We are going to take our units times our grade average. The library study, I had 1 unit and I got a 3.0 in it. And then art, I had a 3-unit course and I got a 2.0 in it. So I'm going to multiply the 3 by the 2.0. And then both the math and the English are both 4 units and I'm multiplying them by 4.0. Or times 4.0. So this ends up being, let's see, 3 plus 6 plus 16 plus 16 over 12. 3541, is that what that top adds up to? 3 plus 6. 41. 41 over 12 is, in terms of GPA, 3.4166. The 6 keeps get repeating, so this would be 3.42. That's the GPA for option 1. Well, this chart doesn't give it a grade for the D minus, but they give a chart for the C minus. That's funny. It's probably like high school. Now let's look at option 2. My C was my 2.0, the B is a 3.0, the A is a 4.0, and the A is a 4.0. So if we're going to do our GPA thing here, I have 1 unit times 4.0 plus 3 units times 4.0 plus 4 units times 3.0 plus 4 units times 2.0. And all of that is divided by 12. So that's 4 plus 12 plus 12 plus 8 over 12, which is 36 over 12, which is 3.00. So option 1's GPA was 3.42, and this one was 3.0. And note, the report card says the same fucking thing. 2 A's, 1 B, 1 C. The GPA is drastically different. So, if push comes to shove, and all your classes like take about the same amount of work, dump the low unit courses first. Worry less about the 3-unit course than the 4-unit course. They frequently have about the same amount of work, but the 3-unit has less impact on your GPA than the 4-unit class. If you're gonna have to like give up on a class and just take the F because you waited to past the withdrawal date. I think the withdrawal date is October 20th. So if you decide to withdraw from a course, you got a long time still, another month and a half. And it just shows up as a W. Where you get your A's, B's, and C's drastically affect your GPA depending on the units in the course. That's the big lesson for 3.3. Then I want to go over a graphing thing. Does anyone want this page up a little bit longer?
Hey, David, I did have a question. I got me thinking. When I graduated high school, I don't know how I remember this 21 years later, but I had 1A, 6 courses, so it's 1A, 4 B's, and a C.
At high school, I think all courses are the same units.
Yeah, and it was well, they always just told me 4.0, 3.0 for the B. The thing you were explaining is the way I always figured it out. I thought it was a 3.0, but I'm trying to figure out what my final GPA was.
We'd have to work it out.
We can, yeah, I can just.
All right, so student asks. This is in 2.4. Following graph shows the median earnings for females from 2005 to 2009 in constant $2009. This means like not accounting for inflation kind of thing. And then part B says redraw the graph so it's not misleading. So if I look at this, what's misleading about it? The lowest line starts at 34,500. Now, the quick and easy way of figuring out which one it is is these pillars have just gotten taller because they go down to 0. But their heights relative to each other should be the same. So the one on the right should be the tallest. And that means D is immediately eliminated because they all have the same height. And then the third one should be just almost as high, where the fourth one is much lower. So it's a little hard to tell, but like C looks like it meets that criteria. A, maybe it looks like it's a little bit lower. But B here, no. The fourth bar is higher than the third bar, and it's not on the big graph. So B's out, D's out. We got to come over here and kind of look at 1, 2, and 3. And now, like, 1 is taller than 2. That works there. And 3 is taller than both of them. And then 4, C looks like a good candidate as well. And like A is just really hard to fucking tell. It looks like if I blow A up, the left one's a little bit taller. Like it's a little bit taller. And that one's like a little bit below the gray line. And these are a little hard to tell. But let's go back and look at the other one. Let's blow up the numbers on this one. So C was the other one in question. Ooh. Now they have the same height thing, but now let's look at the numbers on the left. This looks like if this is 0 and this is 10,000, then every bar in between is like halfway, so like 5,000. So this is 5,000, halfway between 10 and 20 is 15,000. Halfway between 20 and 30 is 25,000. This says 2005 and 2006 were less than 25,000. But the actual graph, both of them are above 34,000. So C can be eliminated as well. A is actually a little hard to see, but through process of elimination, like these are all this, like this is 30,000, this is 35,000. So all of these are close to 35,000 or a little bit higher. And that matches up with what we see over here. So it's the scale on the left that you really got to watch. 2 of them we were able to eliminate just because the bars didn't have the same relative height with each other. I actually don't know that there's a harder way to do that. Like you would have to try to draw them out using the values right here. Like make a big sketch, make one that shows those values. But the problem is the shapes are still going to look like, I went too big on that one. I can't make it go back down. All right, well, let's bring this one out to action. Like to me, this one visually looks better. But the numbers on the left don't support it.
I guess even going back one step further, for me, what I'm still just not understanding is why the graph with the baseline at 34, 35 is not appropriate, because the years in question are represented
Well,
graph.
hold on, let's take, this is probably maybe 34,700. And this might be 36,400 or something like that. They are less than 2,000 apart. Literally less than 2,000 apart on something that's 30,000. They're all over 30,000, which means it's less than 10%. It's more like there's less than like a 7% difference. The high sizes of the graphs, the shortest and the tallest one should maybe only look a little bit taller than the shortest one.
Okay.
Because the relative comparison of the values is like way up. if if it was 1,000 was the base and we had like, and it went up to 3,000. Then we can see the, one of them's like triple the other.
Yeah,
But here. If you start like actually looking at the values. One's not even 30, it's like not even 37. 36.4. And 34 like 6.
yes,
So this is like 400 here, another 500 is 900. That's like 1,400, maybe 1,700 difference between the two,
yeah.
which is about 5%, it's under 5%. So the heights of the bar, like, it should be hard to identify the difference of 5% heights of bars,
Thank you so much.
right?
Yes.
That's just between this, well, maybe not 5%, but that's the smallest and the tallest. All of them, you could easily see which ones were smallest and tallest.
Okay,
It's the middle ones that like. How high are the other ones relative to it?
yeah, okay, I wasn't thinking outside of the box, I kept honing in on, well, it's showing what
Right,
it is from 2005 to 2009, but.
Right.
Seeing why is that not?
like this one, it looks like this one is like 2/3 of that one. It's like if we cut this one into three, the one on the right, the 2006 only has 2 of them. So it's like 30% smaller.
Yeah, yeah.
But-
exactly.
But if we look at the actual numbers, they're not 30% different.
Okay,
So it all boiled down to that y-axis, the numbers on the left. That's it for the class, and the extra bonus question. That's from 2.4 homework number 3. If you're already on 2.4, good job, you're staying caught up. If you're like still doing chapter 1, better hurry the fuck up. All right. Any other questions? GTFO. Unless you're gonna work on homework in here.